So in today's lecture, we're going to talk about some of the most important concepts in modern physics, work and energy. You've most likely heard both of these terms in everyday life, right? People go to work, drinking coffee gives me energy, so on and so forth. But here in physics, these terms have technical definitions, which we will see in a little bit. So what's all the fuss, right? Why should we care about these concepts called work and energy? Well, one advantage of these things is that both the work being done on or by an object, as well as the energy of an object, are both scalar quantities, right? They're just numbers. We don't have to worry about the direction of energy at work because they're just numbers. There's a second, even more important advantage to work and energy, but we will see that later on in this lecture. So for now, let's just get familiar with our first technical definition, right? We're going to start off by talking about the concept of work. So work is defined by W, right? Not to be confused with weight. So it's going to be the inner product, and don't worry, I'll define all these things in a bit. It's the inner product of a force and a displacement. So this is going to be equal to the magnitude of the force, times the magnitude of the displacement times cosine of theta. So this is just F times D times cosine of theta. We just box this off. So this is our first definition. Okay. So this here is our net force. That's our net force. This part here is our displacement. Right, our displacement magnitude. And this thing here, I scroll down just a little bit. This dot here is not multiplication, but it actually stands for something called an inner product. Which is one of the ways that we can sort of multiply two vectors together, but you don't really have to worry about that too much. So what about this theta here? This theta is going to be the angle between our net force vector and our displacement vector. Okay. So the units of work, scroll down a little bit. So the units of work are newtons times meters, right? Because if we look at our definition for work, it's equal to FD cosine theta, right? So F has units of newtons, and our displacement is going to have units of distance. So it's going to have units of Newton times meters. But this is what we call a joule, indicated by a capital J. So this is a joule, right? In honor of the physicist who made a lot of contributions to work and energy and stuff like that. So let's look at our first example of work. So example 1. All right, so in example 1, the problem wants us to find the work done. Find the work done by a force of 60 newtons exerted on a box. Exerted on a box at an angle of 30 degrees. At an angle of 30 degrees for a distance of 100 meters. Right. So we have this picture here. And right now we're looking at a box. And we're looking at a particular force. So this is the center of our box. We have this force F, which in this case has a magnitude of 60 newtons. And its angle here's 30 degrees. And this box moves, 100 meters off to the right or whatever. So its total displacement, right, the total distance that it ends up traveling is 100 meters. So our displacement vector, right, is in this direction. So this is our displacement D, right? And, if I was drawing this more accurately, I would draw this all the way over here, but I'm not for, illustrative purposes. Switch back. So let's find the work done by the force. So the work done by this force in moving this box from here to here, right? The work done is equal to the magnitude of the force times the magnitude of the displacement times cosine of the angle in between. And so this is just F times D times cosine theta. So the work done is equal to the magnitude F, which is 60 newtons, times the magnitude of our displacement, which is 100 meters. 100 meters times cosine of the angle between our force vector and our displacement. Now in this case, that angle is 30 degrees. 30 degrees. And so the work done in moving the box from here to here using that force, right, is going to be 5,196 joules. 5,196 joules. So that's the answer for this first example. And for good measure, let's look at one more example of work. So example 2. Example 2. All right, so example 2 talks about a car. So example 2 says that a car with mass of 500 kilograms, a car with mass 500 kilograms accelerates from rest, accelerates from rest, and reaches a velocity of 20 meters per second. Reaches a velocity of 20 meters per second in 10 seconds. 10 seconds, right? So this is a one-dimensional problem. So the problem wants us to find the work done by the car. So find the work done. By the car engine. By the car engine to move the car during this 10 seconds. To move the car during these 10 seconds. So we know that our definition of work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force being applied and the displacement. Now the problem is that we don't know the magnitude of the force. We don't know our displacement. Right, we don't know the magnitude of the displacement. Get rid of that. And we don't know what our theta is. So right off the bat, it seems like we hit a little bit of a snag, but let's not worry. Because if we remember, we did some of this stuff back in chapter, or like our second lecture. Yeah. Right. So in one-dimensional motion, you remember that the final velocity of an object is equal to the initial velocity of an object plus its acceleration times time. Right. So in this problem, we do know, right? We do know that the car starts from rest and then it reaches a final velocity of 20 meters per second, and it does this in 10 seconds. So using this information, right, this equation becomes our final velocity, which is 20 meters per second. It's equal to our initial velocity, 0 meters per second, plus our acceleration, a, times time, which is 10 seconds, right? So if we solve this, right, so 0 is, obviously don't have to worry about that. So if we divide both sides by 10 seconds, we get that our acceleration for this problem is 2 meters per second squared. Right? And so the net force on our problem is the thing that is providing this acceleration, right? This is our net acceleration for a car. And so the net force on our car is equal to the mass, call this net. So net force is equal to the mass of the car times the car's net acceleration. So this is going to be equal to the car's mass, which is 500 kilograms, times the car's acceleration, which is 2 meters per second squared. So we get a net force magnitude of 1,000 newtons. So this is our F. So F is 1,000 newtons, right? So now we need to figure out how far the car went. So for our displacement, we know that the distance, or the displacement in the x direction, is equal to our initial velocity in the x direction times time plus 1/2 times our acceleration in the x direction times time squared. Right? But our initial velocity in the x direction, or any direction, is 0. Right? Because this thing starts from rest. And furthermore, we know that this acceleration, this one right here, is just 2 meters per second squared. Right? It's what we found in this part right here. And we know all this happens in 10 seconds. So we can figure out that our displacement, let me switch out to different color, our displacement is equal to 1/2 times our acceleration times time squared. So this is equal to 100 meters. Right? So the magnitude, d in this case, is just the magnitude of our displacement. So it's just 100 meters. So now we found d. 100 meters. So what about the angle? Right? In our case, the car, right, is being accelerated forward by the net force generated by the engine, right? And so it's being displaced also in the same direction because of this force, right? So its displacement and the direction of the net force is in the same direction. So in this case, we would say that theta is equal to 0. Right? Because they're both pointing in the exact same direction. So the work done in accelerating, or the work done by the car's engine in accelerating this car, is FD cosine theta, right? Where F is 1,000 newtons net force. The displacement was 100 meters. We have cosine of our angle, which is 0 degrees. The cosine of 0 degrees is just 1. So the work done by this car's engine is 100,000 joules. Right? And that's the answer to our second problem. So work is all well and good as a standalone concept, but its true power comes from its relationship with energy. So up next, we'll talk about one of the most useful and powerful theorems in a physics course, which is called the work-energy theorem. But before that, we'll need to first define something called the kinetic energy. So our next section is going to be the work-energy theorem. Work-energy theorem. And kinetic energy. Here's a little pro tip. Whenever you see a theorem that has something hyphenated like this, right, in this case, the work-energy theorem, that should let you know that somehow work and energy are going to be related. So first, let's start off by defining kinetic energy before we talk about the work-energy theorem, because we haven't really talked about energy yet. So as a definition, we're going to define the kinetic energy. Right, the kinetic energy of an object, we're going to call Ke for kinetic energy. And that's equal to 1/2 times the mass of the object times the speed of the object squared. So the magnitude of the velocity squared. And it's going to have units of joules, right? So you'll notice that energy, at least the kinetic energy, has the same units as the units of work, right? So right off the bat, that should immediately tell you that they're somehow related with one another. And so the kinetic energy of an object, right, is equal to 1/2 times the mass of the object times the velocity of the object squared, right? Or the magnitude of the object, the magnitude of the velocity of an object squared. So if you want to increase your kinetic energy, you either need to have more mass or you need to be moving faster. We can think of kinetic energy as the energy an object has just by being in motion, right? So the heavier an object is, or the faster that an object is moving, the larger the kinetic energy that object will possess. So let's look at a quick example of kinetic energy. So this is going to be example 3. So example 3. So example 3 says that a ball of mass 4 kilograms, ball of mass 4 kilograms is thrown upward, with a velocity of 10 meters per second. With a velocity of 10 meters per second. So the problem wants us to find its kinetic energy. Find its kinetic energy at A, the initial time. So the initial time, so just as it's being launched. B, at max height. In part C, right, 1 second after being thrown. All right. So in this case, our mass is 4 kilograms. And our initial velocity is going to be 10 meters per second. So part A tells us to find the kinetic energy of this thing at the initial time. So it's going to be 1/2 times the mass of the ball times the initial velocity of the ball squared. All right, so plugging this stuff in, we have 1/2 times the mass, which is 4 kilograms, times the initial velocity of the ball, which is 10 meters per second. We're going to square that. And this becomes 200 joules. So this is the kinetic energy of our ball for part A, right? Just as it's being thrown. So for part B, the kinetic energy at the max height of this, ball's trajectory, it's going to be 1/2 times the mass times v squared. But if you'll remember, at maximum height, the y component of our velocity will be 0. So this will be 1/2 times the mass of the ball times the velocity in the y direction at max height. So it has no component of the velocity in the x direction because this ball is being thrown straight upwards in the y direction. So there's no x component to our initial velocity. So at max height, its final speed will be 0 meters per second squared, right? And so we have 1/2 times 4 times 0 squared. Well, that's just going to be 0 joules. OJ. Right? And that makes sense because the kinetic energy is the energy attributed to an object in motion. If the object is not moving, such as when this ball reaches maximum height, then it will have 0 kinetic energy. And so last but not least, we have part C, which is asking for the kinetic energy of the ball 1 second after being thrown upwards. So to solve this, we first need to figure out its velocity at that point. But we know that its velocity is equal to its initial velocity plus the acceleration times time, right? So its final velocity, the thing that we're looking for, is equal to its initial velocity, which is 10 meters per second, plus its acceleration, which is just the acceleration due to gravity, so minus 9.8 meters per second squared, times time, which in this case is just 1 second. So we are going to get a velocity of 0.2 meters per second. So 0.2 meters per second upwards. Right, so this is the velocity of the ball 1 second after being thrown. So now the kinetic energy of this ball, right at this point, is 1/2 times the mass times the final velocity squared. So this is going to be 1/2 times the mass of the ball, which is 4 kilograms, times, the velocity after 1 second, which is 0.2 meters per second. We're going to square that. So our kinetic energy, in this case, is going to be 0.08 joules. Right, so just a few examples of trying to calculate kinetic energy. So now that we've seen the concept of work and kinetic energy, we can finally state the remarkably important work energy theorem. So the work energy theorem, the work energy theorem says that the net work done on an object, and I'll talk about that. So the net work done on an object is equal to the change in that object's kinetic energy, which is its final kinetic energy minus its initial kinetic energy. So this is going to be 1/2 m v final squared minus 1/2 mv initial squared. So this is the work energy theorem. And this is important because on the one side, it gives us a relationship between the work done on an object, and it gives us a relationship to the change in kinetic energy of that object, right? And remember, the kinetic energy is just the energy associated to an object in motion. So this really tells us, when we do some amount of net work on an object, the object's kinetic energy will change, right? It'll move faster or slower, depending on what our network is, or if our network is 0, it won't change at all. So what do I mean by this net work done here? So the network, write this down here. W net is the network done on an object, right? And the way that you calculate that is you just add up the work done by all the forces acting on the object. Right, so as an example, if we have a box like so, let's say that there are 3 forces acting on the box. This is the center of the box. Let's say that there's a force F1, points like this. Let's say that there's a force F2, maybe points over here. Maybe there's a force F3 that points kind of downish like this. Right? Then the net work done. So the net work done by all the forces acting on this box is just the work done by force 1, by this one, plus the work done by force 2, this case, plus the work done by force 3, right, as an example. So in order to figure out, what these works are, right, we need to know the magnitudes of F1, F2, and F3. We need to know how strong these forces are, but we also need to know what the displacement of this box ends up being, right? So if we end up learning that the box, ends up being displaced this way, for example, right, then, we can calculate, all these different angles between our forces. And then, we can actually calculate the work done by each of these forces. And then the network is when you just add all of them together. So that's all that this term right here is saying. So let's look at a problem. So this is going to be example 4. So example 4. So example 4 says that it takes 185 kilojoules of work. It takes 185 kilojoules of work to accelerate a car from 23 meters per second to 28 meters per second. Right? Problem is asking, what is the car's mass? What is the car's mass? So the work done is equal to the change in kinetic energy, right, which is 1/2 the mass of the car times the car's final velocity squared, minus 1/2 times the mass of the car times the car's initial velocity squared, right? And so we're trying to find mass, but the mass of the car doesn't change. So this is going to be, right? So we notice that this is the same mass in each term. It's going to be 1/2 times the mass of our car times the final velocity squared minus the initial velocity squared, right? So on the left-hand side, we have the work done. So the work done is 185 kilojoules, right? So a kilojoule is 1,000 joules. So the work actually done is 185,000 joules. And on the right, we have 1/2 times the mass of the car, right? We're trying to look for this thing, trying to look for this mass right here. And we have the final velocity of this thing squared was 28 meters per second. We're going to square that. We're going to subtract off from that the initial velocity of the car squared, which is 23 meters per second squared. And so when you solve this, right, if you multiply both sides by 2 to get rid of this 1/2, and then you divide both sides by this thing in parentheses, you get that the mass of the car is 145 kilograms. Which admittedly is a very light car. All right, let's look at one more problem. So we have example 5. Example 5. So in example 5, this problem says that a 16 kilogram sled is being pulled along, the horizontal snow-covered ground. Horizontal snow-covered ground by horizontal force of 24 newtons. By a horizontal force of 24 newtons. So starting from rest, the sled attains a speed. The sled attains a speed of 2 meters per second. Of 2 meters per second in 8 meters. All right, so this thing starts from rest, and we got this horizontal, pushing or pulling force, and then in 8 meters, this thing reaches a speed of 2 meters per second. So what's that? That's what that means. So the problem goes on to say, find the coefficient of kinetic friction. So find the coefficient of kinetic friction between the runners of the sled and the snow. So I guess between the sled and the snow. Okay. So we're going to solve this problem in 2 ways. So the first way, we're going to call method 1. So method 1. All right, so in method 1, we're going to draw our free body diagram of our box. So here's the ground. Here's our box. Right. We're going to draw our x-axis. parallel to the ground like this. Our vertical axis is going to be our y-axis. This is y. Now we're going to draw on our forces. So there's the normal force of the snow pushing up on the box. Force. There's the pulling force that's dragging the sled along to the right, call it F. There's the weight of the box that pulls straight down towards the center of the earth, mg. And last but not least, if the box is going to the right, or the sled is going to the right, there's the friction force that is opposing that motion, right? And so for the sake of this problem, we are assuming that this box, the displacement is going to be, maybe I shouldn't use green, pick a different color. So the displacement in this case is pulling our box to the right. So first things first, let's try and find the net work done by each of the forces on this box. So let's calculate the work done by the force F. That's going to be F times the displacement times cosine of the angle between our pulling force F and our displacement. Well, our pulling force F and our displacement are both in the same direction, right? They're both going directly to the right. So in this case, this is going to be the magnitude of the pulling force, which is 24 newtons, times the displacement, which the problem tells us is 8 meters, times cosine of 0 degrees. The work done, in this case by the pulling force, is 192 joules. 192 joules. So what about the normal force? So the work done by the normal force is equal to the magnitude of the normal force times our displacement times cosine of the angle between them. Right, but notice that the angle between them, right, the displacement is in the positive x direction, our normal force is in the positive y direction, and there's an angle of 90 degrees between them. So this is going to be 10 times 8 meters times cosine of 90 degrees. But cosine of 90 degrees is 0. So it does 0 work in moving the box from here 8 meters to the right. So that's an important point, and one that I haven't really talked about yet. If a force is perpendicular to the displacement of the object, then by definition, that object does no work. Right? So in this case, if our displacement is to the right, notice that our normal force is perpendicular to it, right? It's off by 90 degrees, but also that our weight is also off by, in this case, minus 90 degrees, right? It's perpendicular to the direction of motion. So both the normal force and the weight mg do not do any work. So I'll call the work done by the weight W sub W. Right. It's going to be the magnitude of the weight times the displacement times cosine. In this case, we're going to call this negative 90 degrees because we're starting from the positive x-axis, and then we're going clockwise, which means negative 90. Negative 90 degrees. But this is still 0 joules, right? 0 joules of work done by the weight in this case. And so last but not least, we have the work done by the kinetic frictional force. So it's going to be equal to the magnitude of the kinetic frictional force times the displacement times cosine of the angle between them. So the magnitude of the kinetic frictional force is v sub k times the normal force. Our displacement is still 8 meters. And cosine of our angle this time, right? Our displacement is in the positive x direction. Our kinetic frictional force is in the negative x direction. And so the angle is going to be 180 degrees. So this is 180 degrees. And so the work done by the kinetic frictional force is just going to be minus kinetic frictional, or coefficient of kinetic friction, times the normal force, right, times 8 meters. So again, in this problem, we're trying to find the coefficient of a kinetic friction between the sled and the snow. So really, we're trying to find this coefficient mu sub k here, right? So we've calculated the work done by every single force in this problem, and we can use the work energy theorem to add all these together, and that'll tell us the change in our kinetic energy, right? So the net work done is just the work done by adding all these works together. So it's the work done by the force F, the work done by the normal force, the work done by the weight, plus the work done by the kinetic energy. But since the work done by our normal force and the work done by our weight are 0, both these terms fall out. And so the net work done in moving this sled is equal to the work done by the force, which is 192 joules, plus the work done by the kinetic frictional force. So it's going to be plus this, which in this case is going to be minus E sub k times the normal force magnitude times 8 meters, excuse me, 8 meters, right? So that's the net work done. But according to the work energy theorem, the net work done is equal to the change in kinetic energy of an object. So it's the final kinetic energy of an object minus the initial kinetic energy of an object. Right? So if you remember back at the beginning of the problem, this sled has a mass of 16 kilograms, but it starts from rest. So its initial velocity is 0, and it attains a final speed of 2 meters per second. So since its initial velocity is 0, 0 squared is 0, because this is 0. So the change in kinetic energy is just equal to the final kinetic energy, half mv final squared. Right, but this is going to be equal to 1/2 times the mass of the sled, which is 16 kilograms, times the final velocity of this sled squared, which is 2 meters per second squared. So the change in kinetic energy of this sled, right, is just 1/2 times 16, which is 8, times 2 squared, which is 4. So 4 times 8 is 32. It's going to be 32 joules. And so we know that the net work done is going to be 192 joules minus coefficient of kinetic friction times our normal force magnitude, right, times 8 meters. And that's going to be equal to our change in kinetic energy, which is just 32 joules. Right? Well, I can subtract off 32 joules from both sides, and then I can move this whole term over by adding it to both sides. So on the left-hand side, we're going to have 160 joules. Then on the right, we're going to have coefficient of kinetic friction, the thing we're looking for, multiplied by the normal force, times 8 meters. So I can divide both sides by 8 meters. So the left-hand side becomes 20 newtons is equal to coefficient of kinetic friction times our normal force. And so if we could figure out what the magnitude of our normal force is, we'll be golden. We can figure out what this coefficient is. So let's do that real quick. So looking at our picture here, right? If we use Newton's second law in the y direction, and we just add up all the forces in the y direction, we have that our normal force is in the y direction, and our weight is in the negative y direction. And they are the only two forces that act in the y direction. So when we look at the sum of the forces in the y direction, it's going to be equal to the mass of the sled times the sled's net acceleration in the y direction. But we don't want this sled taking off like an airplane or burrowing into the ground like a mole. I don't know. So we want the acceleration in the y direction to be 0, which means the right-hand side of this whole thing is going to be 0. Then on the left-hand side, we have the normal force pointing in the positive y direction minus the weight of the sled pointing in the negative y direction. All that's equal to 0. So we see that the normal force is equal in magnitude to the weight of the sled. Right? So the weight of the sled is just 16 kilograms times g, which is 9.8 meters per second squared. So this gives us a normal force magnitude of 156.8 newtons. Right. So going back up here, we see that our coefficient of kinetic friction times our normal force is equal to 20 newtons. So if I divide both sides by the magnitude of normal force, we see that our coefficient of kinetic friction between our sled and the snow is going to be equal to 20 newtons divided by the magnitude of our normal force. So it's going to be 20 newtons, right, divided by 156.8 newtons. We get that the coefficient of kinetic friction between our sled and the snow is equal to about 0.13. Right, so this is our first method of solving this. We use the work energy theorem and the net work done on an object in order to figure out, what we needed to figure out, which in this case was the coefficient of kinetic friction. But let's try a second way. Right, so this is going to be called method 2, right? And method 2 is just, using the stuff that we knew before. So for example, we know that the final velocity of an object squared minus the initial velocity of an object squared, right? All this is in the x direction, is equal to 2. Let me just call it this. It's actually more consistent. This is equal to 2 times our acceleration in the x direction times our displacement in the x direction, right? So our final velocity in the x direction is 2 meters per second. Our initial velocity in the x direction is 0 meters per second. And we have 2 times our acceleration, whichever, whatever that is, we don't know that yet, times our displacement, which in this case is 8 meters. Okay. So 0 squared is just 0. And then 2 times 8 is 16. So we have that A, our acceleration in the x direction, is going to be equal to 4 divided by 16 meters per second squared, right? Because on the left-hand side, we have 2 squared, which is 4. And then we're dividing both sides, by 2 times 8, which is 16. So this is going to be an acceleration in the x direction of 0.25 meters per second squared, right? And so we know that when we add up all the forces in the x direction, that needs to be equal to the mass of the sled times the sled's net acceleration in the x direction. But going back up to our picture, there's only 2 forces acting in the x direction. There's our pulling force, and then there's the kinetic frictional force pointing in the opposite direction. So we have our pulling force minus our kinetic frictional force. That's equal to the mass of the sled times the sled's net acceleration. Right. But we can solve this, right? Because we know what the magnitude of this pulling force is. It's going to be, 24 newtons, right? So F is just a magnitude of 24 newtons. And we know that the magnitude, for our kinetic friction force is just the coefficient of kinetic friction times our normal force magnitude. And that's going to be equal to the mass of our sled, which is 16 kilograms, times the net acceleration of our sled, which is just 0.25 meters per second squared in the x direction. So if I move this term over and I subtract off this term from both sides, we get that, again, coefficient of kinetic friction times our normal force is equal to 20 newtons. And you'll notice at this point, what we have here is basically the same thing that we had in the method that we did just before this one, right? So the way that we solve this is going to be exactly the same, right? We find out what the normal force is. In this case, we find that it's 156.8 newtons. We divide both sides by that magnitude, and then we're going to get, again, a coefficient of kinetic friction of about 0.13. Right, so we could have done either. The fact that there's multiple ways to solve this sort of problem gives us a little bit of flexibility whenever we're trying to solve these problems, right? Because the more ways you have of solving a problem, the better. So we're almost ready to talk about the second main advantage of work and energy, right? But we have one more step to go before we get there. We first need to talk about gravitational potential energy. So we're going to talk about gravitational. Again, don't want to be writing with a highlighter. So we're talking about gravitational potential energy. Right? So the gravitational potential energy is just the work done by the force of gravity. So work done by the force of gravity. Right? So if you have, if this is the ground, for example, we have an object that starts from up here, for example. Right, so this is going to be some initial height h naught. Okay, well, this thing refuses to work with me, so I'm just going to have to draw by hand. So this distance here is the initial height of our object, whatever that is. And the object is going to experience a weight. So it's going to experience the force of gravity between that object and the ground. So this is just the force mg pointing down. And then let's say that, the gravitational force moves the object from here down to like here, for example. So it moves it down to here. So let's say that this height right here is our final height, hf. Right? So we can calculate the work done by gravity, because the work done by gravity is equal to the force of gravity times the displacement times cosine of theta. Right, so in this case, the force of gravity is pointing downwards, and our displacement is also going downwards. So in this case, this angle theta here is going to be 0. Right, so this is equal to the magnitude of our gravitational force times the magnitude of our displacement. Now keep in mind, even though our displacement is our final position, right, minus our initial position, this is the magnitude of it. So we want this to be the positive value. And so that magnitude is going to be our initial height minus our final height. Right, and then cosine, in this case, is going to be 0. Or cosine of 0 is going to be 1. Right. So ultimately, the work done by gravity right, if we multiply this mg through, we have mg times h naught, right, our initial height, minus mg hf. So this thing here, right, this right here, we're going to call this first term. Zoom in a little bit. We're going to call this first term our initial gravitational potential energy. It's going to be our initial gravitational potential energy. Right. So we're going to call that PE0. And like you might expect, this term right here is going to be our final gravitational potential energy. This is our final gravitational potential energy. Right, which we're going to call PEF, right, PE final. So from this comes a definition. So we're going to define the potential energy of an object, or the gravitational potential energy of an object, to be equal to its mass times the acceleration due to gravity times its height above the surface of the ground. So this is our gravitational potential energy, right? So before we talked about kinetic energy, and this is sort of its counterpart, potential energy. If I could just draw a box. There we go. Yeah. And just like kinetic energy, this is going to have units of joules. Units of joules. So let's look at a problem. So this is going to be, last example we did was example 5. So this is going to be example 6. So for example 6, example 6 says that a ball with mass 2 kilograms, a ball with mass 2 kilograms is thrown upward from the surface of the earth. Is thrown upwards from the surface of the earth. Right. It reaches max height of 10 meters. It reaches a max height of 10 meters. So the problem wants us to find the work done by gravity from the point thrown to max height. So find the work done, by gravity from the point of thrown, to max height. So the work done by gravity, is equal to mgh naught minus mghf. Right, so the mass is 2 kilograms. So we have 2 kilograms times the acceleration due to gravity, so 9.8 meters per second squared, times our initial height above the surface of the earth. So we're going to call that, we're going to call the ground a height of 0. So it's going to be 0 meters. So it's going to be this minus mgh naught, or mghf. So minus 2 kilograms times 9.8 meters per second squared times its final height of 10 meters above the ground. So this first term is going to be 0 because we're multiplying through by 0, right? So the work done by gravity in this case, work done by gravity is going to be equal to minus 196 joules. So that's the whole problem. All right. Now, the last thing before we really make full use of energy and work and all that stuff, I need to define the conservative forces. So definition. Conservative forces. Right. So there's two versions. I'll give you both. So version 1 says that a force is conservative. A force is conservative when the work done, or when the work it does, when the work it does on a moving object, is independent of the path between the object's initial and final positions. So it's independent of the path between the object's initial and final positions. Right, that's version 1. So that says, if you have got an object initially here, position, and then you have another object, or like it then it moves through some forces or whatever, and it somehow gets to this final position. This is saying that if the forces that are acting on this thing to move it from here to here are conservative forces, and this is saying it doesn't matter if the object goes from here to here, or if the object took a weird path like this, or there's a whole bunch of funny business for eventually getting back to this point here, right? If the force is conservative, then the work it does, right, the work that this conservative force does in moving the object from here to here won't matter depending on path. So not the most useful for you guys right now. Let's look at the second version of the definition for conservative forces. So a force is conservative. So a force is conservative when it does no net work. When it does no net work on an object moving around a closed path, being around a closed path, starting and finishing at the same point. So that's what the definition of a closed path is. It's when something starts and ends at the same spot. So starting and ending at the same position. So the gravitational forces. So gravitational forces, they are conservative. Friction forces are not conservative. Right, because look, if we look back at the definition for the work done by the gravitational force, right? According to one of the definitions for conservative forces, if the starting point and the ending point for our object is exactly the same, then that's saying that the net work done by the force of gravity is 0, right? So that means that this is a conservative force. Right? Where friction forces, on the other hand, right? The friction force always points in the direction opposite to the intended motion of an object. So looking at this example, so if there's friction, right, if we're moving an object from here to here, right, it kind of depends on the path that we take if we have to take friction into account. Because if we move the box from here to here, for example, then, you know, the friction force is going to be doing some work the entire way. And likewise, if we go around a longer path, then the friction force is going to be doing work along that whole path. And so it's going to be doing more net work the longer that path is. So by definition, this is not a conservative force. So the reason why we call these things conservative forces or non-conservative forces brings us to our next topic. So we're going to call this next topic the conservation of mechanical energy. So this is the second main advantage for work and energy. So the conservation of work, let me capitalize that, work and energy. So we need to define, there's a lot of definitions, but we're going to define the total energy of an object to equal to the object's kinetic energy plus the object's potential energy. So this is our definition. So E here stands for the total energy of our object, right? Kinetic energy, KE, it's just, you know, the kinetic energy, right? It's the energy associated to an object in motion. Last but not least, the potential energy here, PE, so potential energy. This is most often attributed to the sort of setup of our object, right? So in the case of gravitational potential energy, it's the relationship of our object with respect to the nearest gravitational object, which in this case is the Earth. So the total energy is quite nice because with it, we can do some things. So real quick, the total energy, right? We know that the form for the kinetic energy is 1/2 mv squared, right? And if the only potential energy in our problem comes from the gravitational force, then the gravitational potential energy has a form of mg times our height above the surface of the Earth. And so our total energy ends up with this sort of form, right? And the reason why this is useful is because there's a lot of problems where this total energy is conserved. It's a constant. So we call this the principle of conservation of mechanical energy. So we call this the principle of conservation of mechanical energy. Right, so in certain situations, right, where all the forces in our problem are conservative forces, this means that the total energy of our system is conserved, right? The total energy is going to be a constant. This is important because if you look at, for example, our total energy right here, right? If we're dealing with energy conservation, then what this says is that our object can go, a little bit faster, but in order for that to happen, it needs to go closer to the Earth, right? Because ultimately, the left-hand side of this equation, the total energy, needs to be equal to a constant. And so here's where we start to see the real power of energy. Energy can be transformed from one type of energy to another, right? You can transform kinetic energy into gravitational potential energy. So for example, if you have, a ball that you're throwing upwards, in this case, you're transforming, as the ball goes upwards and reaches its max height, you're initially transforming all of your kinetic energy into potential energy. Or, if you're dropping something off the side of a cliff, right, and then you're throwing something off the side of a cliff like this, right, you're transforming potential energy at the top of the cliff, transforming potential energy into kinetic energy. And we can use this to great effect when we're solving problems, right? There's a lot of difficult problems out there that when you do the conservation of energy with them, they become much, much easier. So let's look at a problem. So last problem for the day, we have example 7. So in example 7, this says that a ball with mass of 2 kilograms, a ball of mass 2 kilograms is thrown upward from the surface of the Earth. It's thrown upwards from the surface of the Earth with initial velocity of 10 meters per second. So the problem wants us to find the max height. Find the max height. Right, so we already did this problem earlier, right, where we looked at our final velocity in the y direction minus our initial velocity in the y direction. It's going to be equal to 2 times our acceleration in the y direction times our displacement, right? So that's one way we could solve it. Let's call this method 1. Right? So if we want to find max height, we could punch in that this final height at max height is going to be 0. This will be 10. And we can solve for our displacement in the y direction. So, or we could use conservation of energy. So the only force that's acting on this ball is the force of gravity, which is a conservative force. So the energy throughout the entire trajectory of this ball being thrown up, right, the energy of this ball is conserved. So using method 2, right, we're going to be using energy. So the initial energy of the ball is its initial kinetic energy plus its initial potential energy. Right, that's 1/2 times its initial velocity squared plus mg times its initial height. but it's being thrown from the surface of the Earth, right? So its initial height is 0. So this term is gone. And so the initial velocity, or excuse me, the initial energy is entirely kinetic energy. So this is going to be 1/2 times the mass of the ball times the initial velocity of the ball squared. Just like that. Right, so this is going to be 100 joules. Right. Now, if we look at the final energy, the final energy is going to be 1/2 mv final squared at max height plus the gravitational potential energy at max height. Right, but at max height, its velocity in the y direction is 0, and since it's moving entirely in the y direction, the magnitude of its velocity is going to be 0. So this term is gone. And at max height, all of the energy of this ball is gravitational potential energy. So this is just the mass of the ball, kilograms, times the acceleration due to gravity, times max height. And because we know that energy is conserved here, we know that our initial energy of our ball is equal to our final energy. So our initial energy is 100 joules. And on the right side, we have our final energy, which is, 2 times 9.8 times our final height above the ground. So 2 times 9.8 is 19.6 units a meter per second squared. Or newtons, excuse me. Newtons times our max height above the ground. And now if we divide both sides by 19.6, we get a max height of 5.1 meters. So at this point, you might look at these two methods and say, well, they look, kind of the same. In fact, this one actually might seem a little bit shorter than this one. But here's the thing. This second method still works even when the problem is really, really complicated. So we'll see some examples during, problem solving where it would be a nightmare, an absolute nightmare to have to try and use the stuff that we learned in the first week and a half of this course to try and find, whatever the problem is asking us to find. But the advantage of using this second method is that, given certain situations, very, very difficult problems actually become very, very easy. And so we'll see some of that stuff on Thursday. But for now, that's all I've got for you guys today.